Here we go. This is 2014, problem number 4 for both Calculus AB and BC. And some of you might be thinking in your head, I thought you said that we're not going to have problems with velocity, acceleration, and position. That's partially true. You're not going to have integration problems involving that. But you will have problems where you find the derivative or apply what you know about just basic calculus principles. So if there's part of this that won't be on the test, I'll let you know. For my BC kids though, all this is fair game because this isn't excluded from the BC. But for you AB people, this year's test, I'll see if there's something you need to use the integration for to find the answer. I don't know. But I want you to make sure that you watch this for part D, because that I believe is a related rate. And I just fear there's going to be a related rate on this year's test. And if there is and you're not practiced on it, that would be very bad. So let's hope that doesn't happen. So let's take a look at this. It's a data table. Train A, so you have the first train. It's going east and west. The velocity is given by VA of t, and that's here. So that's the velocity of train A at specific times. So we need to draw a nice picture. So I have, let me read the other parts real quick. So you're going to have a train A, okay, part B is train B. You have a station. All right, let's do this. So part A, straight up, average acceleration. So we dealt with this earlier. How do you find the average of any function? You have to know the formula. And by now, hopefully you know average acceleration. The average of anything is you integrate. So they want to go from 2 to 8 of acceleration. I'll call it AA of t for acceleration. And you divide by the width. You might want to state, because we haven't defined what AA of t is. So that you don't confuse the grader, I probably should have said that AA of t equals the derivative of the velocity. Acceleration, derivative of the velocity. So let that. So I'm going to state what the A is. So that's your formula for average of anything. Now using the fundamental theorem, your first step is you take the antiderivative of A of t. Clearly, that's just V of t or VA of t. And then they say, fundamental theorem, you plug in 2 and you plug in 8. And that's over 6. Then that's going to be VA of 8 minus VA of 2 over 6. And I plug in those values from the table. VA of 8 is negative 120. VA of 2 is 100 all over 6. Am I done? Let me read the question. I am done. That's the answer for part A. So again, just recognizing key words, average, not average rate of change, average function you have to know. And there it is. I know you physics people like using formulas, but I'd rather you use your concepts from calculus instead of memorizing physics formulas. B, do the data in the table support the conclusion that train's A velocity is at negative 100 meters per minute at some time t between 5 and 8. So here's 5, here's 8. You want the velocity to be negative 100. So again, when you have a data table problem, your theorems will come into play. Intermediate value theorem, extreme value theorem, and mean value theorem. You've got to know those. So the mean value theorem will prove things about the derivative of v, or the acceleration. This is just the velocity, not the derivative. So the intermediate value theorem, what that will show you is that this velocity has to equal a number. And if you look, negative 100, if you go from 40 to negative 100 to 120, you have to cross negative 100. That is clearly the intermediate value theorem. So that's what we're doing for B. I'll place it right here. So what must be true for the intermediate value theorem to work? The only condition that it must be continuous. Now, if we read the original question, and I didn't do one of my rules, we're supposed to write down all the known information. So I should have said earlier that v of a is differentiable. Nowhere in the description does it say it's continuous, but we have what we need to know. Since VA of t is differentiable, therefore VA of t is continuous. That's actually a theorem that you're supposed to know. But logically it should make sense because we know when is a function not differentiable? Sharp points. Okay. The second thing, so we know this has no sharp points. The second, vertical tangent lines. Since it's differentiable, we know it doesn't have vertical tangent lines. And when else is a function not differentiable? If you have a discontinuity. But since it's differentiable, clearly there's no discontinuity. So that's where that statement comes from. Now, here's what we have to do. Let me block this off. We have to show that our magical number, negative 100, is between the value of the function at the endpoints. So what's VA of 5? That is 40, right? That is greater than negative 100, which is greater than the velocity of train A at 8, which is negative 120. Now, technically, you don't need that and that, but I'm just writing it there just because it's easy, and this makes sense. So we have done everything according to the conditions of the intermediate value theorem. We have continuity. We have negative 100 between VA of 5 and VA of 8. Now we're done. Therefore, and I'm not going to write this out, but you're going to write, I will circle it in green. What do they want? Does the data in a table support the conclusion that, so you can say, therefore, all of this, train's A velocity is 100 meters per second at some time t between 5 and 8. So you just copy all that down right there. Just save time, I'm not going to do it, but that's just a hint. Your conclusion, after you show everything that needs to be proven for your conclusion, you just write what they asked for after therefore. So we've done part B. Part C. Okay, part C will not be asked on the A-B test. because you want a final position which involves an integral to get the change in position. But for you BCers, you should pay attention. For you ABers, you can listen, because this applies to other problems that have the fundamental theorem, but if you want to skip through to D, that's fine. I'm going to do part C right here. So at time t, the train's position's 300. That's important. So we have a starting position. And the train is moving to the east. So that's to the right. You want the position of train A. At time 12. So I'm going to do this x sub a. I'm going to do this here off to the side. Let x a of t be the position of the train A. I do that so I'm introducing a new function, so I have to tell them what the function I'm using is. So they want XA at 12. This is the fundamental theorem, so I need to know the starting position. I need to know the position of train A at 2. I use 2 because we know 2. Plus how much the position of the train changes. How do you find that? If you integrate from 2 to 12, VA of t dt, that gives you the change in position of A. So we're starting at 2, we're ending at 12, so I know the position at 2, and then someone tells me how much it changes from 2 to 12, because this is actually x prime of A. Integrate of x prime of A gives you the change in x of A. So that is my formula. Now we want the trapezoidal. So we're going to do a trapezoidal sum. And this is something you need to know anyways for you ABers. Not necessarily in a context of a velocity problem, but in a general context of a data table analysis. So let's do this. XA of 2 is given as 300 right there. Plus, so we're going to do a trapezoidal from 2 to 12, from here to here. So I'm going to do each interval in a different color. So we're going to do these two first. So it's going to be 1/2 the sum of the bases. That's going to be VA of 2 plus VA of 5 times the width. From here to there, it is 3 wide. 1/2, and then the next pair I'm going to do in purple. It's going to be these two. So it's going to be the sum of the bases, which is V5 and V8. And this width here is 3 again. And then the last one I will do in green. No, I have green used. Red. No, I'm going to use the yellow. So we're going to do the last pair. It's going to be 1/2 the sum of the bases, so it's going to be the velocity of train A at 8 plus the velocity of train A at 12, and the width 8 to 12 is 4. All right, just to save time, I'm not going to do this last part, but you would have to rewrite all of this by looking at a table and finding all these values from the table and plugging them in. Do not simplify. That's your answer. You are done. Let's go to the fun part, part D. This is the related rate. So you have a second train that travels north from the origin station. So we have a train station. Choo-choo. There's our building, our train station. Pretty, huh? And then you have train A running left and right. So there's the train track. Choo-choo. And then you have another train running north and south. Choo-choo. And then let's fill in our information. The second train B travels north from the origin. Ooh, I don't even need the stuff below. It's traveling north. Oh, whoa. Sorry. What am I doing? So we only need the north part of this. So we have train B. Here it is. Ready? Train B. Choo-choo. There's train B. It's to the north. And we have its velocity. So the velocity of train B, it has VB of t. And at times t equals 2. So at t equals 2, the train is 400 meters north. This distance is 400. Find the rate in meters per minute at which the distance between A and B are changing at t equals 2. Do we know the position of train A at 2? Ah! Wow, we have that from part C. Look at that. At times t equals 2, train A's position is 300 meters east. So let's get another choo-choo. Choo-choo. There's train A. And we know that this distance is 300 because they tell us in part C. And do we know, what else do we know? Look at our chart. 2 seconds, VA is 100. So I can write that at t equals 2, the velocity of train A is 100. Now, I'm going to rewrite that. No, I think yeah. I'm going to rewrite this. The velocity is the rate of change of the position. It's actually dx dt at t equals 2. Here, let me do this for you. Now, this one, VB at 2, we can plug this 2 in here. Is this a calculator question? No, it's not. No calculator. So plug in 2 there. So VB of 2, that would come out to be 125. So where am I going to write that? I'll just do here. VB of 2, if you plug that in, you get 125. That's important information. And VB, okay, I have to define some stuff here. That is how fast I'm going to do y. That's dy dt at t equals 2, where this distance here is y. So how fast y is changing is VB. How fast x is changing is VA. And then here's what they want to know. Find the rate in meters per minute at which the distance between train A and B is changing. We need to define that, and let's make it green. I like green. So the distance between these two trains is that. And that, what do you want to call that? The distance between the train. I don't want to use D because that'd be ddt. I'm going to use C. Why C? Because trains go choo-choo. That's C. So I'm going to say let C equal the distance between the two trains. All right, so now let's look at this. We have dy dt, dx dt, and what do they want from us? They want the rate, the distance between A and B is changing, train A and B. So the distance, they want how fast C is changing when t equals 2. That's what they want. So our three variables are x, y, and c. Because I called this x, yeah. So we need an equation involving those. Clearly it's a Pythagorean theorem. X squared plus y squared is c squared. Now we need to take the derivative, and you should see that the variable is t. It's not x, it's not y, it's not c, the variable's t. And you got to realize at this point, this is the whole key of related rates. X changes as time changes because the train's moving. So that is actually a function. It's not your variable. X is a function of t. Same thing, y is a function of t. C is a function of t. So when you take the derivative of all of these, it is chain rule. So the derivative of box squared is 2 box times the derivative of box. The derivative of box squared, again, is 2 box times the derivative of box. The derivative of box squared is 2 box times the derivative of box. So I just plug in the values that I know. X is given right here, 300 at that time. dx dt was 100. And it's positive because it's moving right. And dy dt is positive because it's moving up. So it's 2y, they give us here, it's 400. And dy dt is 125 positive because it's moving up. C. To find C, we have to use a Pythagorean theorem. We have x squared plus y squared equals c squared. Well, x squared is 300 squared. Y squared is 400 squared. Now, you should know if it were 3 and 4, the Pythagorean triple is 3, 4, 5, right triangle. Since it's 300, 400, if you calculate C, you're going to get 500. So that is just, you could do it in your head if you understand the Pythagorean triples, or you can do the ugly algebra and work that all out and get 500. So C is going to be 500 dc dt. My last step, I divide everything by that 2 times 500. So dc dt equals, and again, don't simplify. Leave all of this ugliness as it is, especially because this is a non-calculator question. Bam. Bam. Hopefully all that's right. Let's see, the top would be 30,000. I don't want to do that. That's right. It's got to be right. I believe I'm right. I'm not going to simplify that, but if you do, now I'm just getting the answer from the book. The book says it's 80,000 over 500, which is 160. Don't do that. You don't need to do that. But that's the answer. We're done. This is your answer right here. Stop. All right. That's the related rate. I think next week or the following week, we're going to just practice related rates just to be safe, because I know that was an area of weakness. So that's it for this problem. I think we're done for the day, right? That's the third one. Bye.